Okay, hello. So this video is going to go into some technical details of TLSNotary's algorithm to try and, obviously we've got a document. We could call it a white paper, doesn't really matter what you call it, which I'll show here. And this lays out in some detail, or in a reasonable amount of detail, the, let's say, mathematical or cryptographic basis of the TLSNotary algorithm. And of course you can read that as carefully as you like, but I thought it would be a good idea for those who are genuinely interested to understand how it works in detail to present a short video going over some of the ideas. Inevitably I can't cover every detail, but I'll do my best. So I'm going to use this kind of notepad format to explain it. So here I've got 5 areas that I'll cover. We'll start off with TLS itself, because obviously that's the basis of the whole thing. Now, I debated with myself, should I be talking at what kind of level? Should I be just assuming somebody knows everything about TLS? Should I be assuming people know nothing about it? Both extremes seem inappropriate. So I'm going to aim to just give some details, as mentioned here in number 1, of TLS as they relate directly to TLSNotary. So we should think of TLSNotary as a modification of TLS, but not, how to say, it's as it were an addition to TLS. So TLS itself as a protocol is going to operate entirely as normal. I think I can say that theoretically it's an entirely normal operation of TLS. Specifically it's TLS 1.0 or 1.1. I should mention that somewhere. It does not apply to TLS 1.2 because of some technical details. Now, having gone over TLS a little bit, and specifically the pseudorandom function, we're going to examine the additional algorithm steps that TLSNotary puts into that process. And then we're going to address in parts 4 and 5 how we can deal with the way those modifications change things, how we can make sure that, so to speak, it still works as a whole. That's a bit vague and abstract, but that's the best I can do right now. Okay, so TLS itself, what will I say? We'll come back to this. So yeah, some TLS preliminaries. The basic idea of TLS is to make sure that 2 parties, a client and a server, can talk to each other and gain those key cryptographic properties that we like, namely privacy, authentication, so in authentication we include prevention of forgery, as well as identification of the parties involved. So crudely think of it as 2 things. I suppose there's more than 2, but crudely think of it as making the communications private and ensuring or giving proof, if you like, that the person you're speaking to is the person you think you're speaking to. So at the top I've written here, combine asymmetric and symmetric crypto. So asymmetric crypto is sometimes called public key cryptography, and obviously the main point about that is that it enables you to share a secret without sending that secret over the wire. And why do we combine it? Why can't we just use asymmetric crypto, since in asymmetric crypto we can provide encryption? Well, originally it was mainly for performance reasons. Perhaps there are other reasons, I'm not sure, but doing encryption using public key cryptography alone is a bit cumbersome, and so there are certain advantages to using symmetric cryptography. So the concept is very simply a secret is shared using public key cryptography, and then that secret is used to encrypt another secret, so that at the end of the process both parties have this second secret, knowing that no third party has been able to snoop on it, and using that shared secret they encrypt and decrypt their messages between each other. Okay, so it's pretty high level overview, but okay. Specifically in asymmetric cryptography, the two main ways that asymmetric cryptography is performed in TLS are using one of either RSA or, more recently, elliptic curve cryptography. The latter, ECC, has the advantage of being more performant. You're using smaller key sizes, so reducing the computational overhead of the asymmetric crypto part. There are probably other advantages. I'm not an expert by any means. RSA, on the other hand, is the historical basis. It was the first main public key cryptography algorithm, and we're going to be talking a little bit about that in later steps. And so what does the asymmetric cryptography do? It enables the two parties to, to share some secret key. Once they've both got that secret key, which is called the pre-master secret. So master secret should be a name that makes some sense. It's the idea that there is one overarching secret which controls the entire TLS session. Pre-master, and the reason it's called pre-master is because there's an intermediate step between getting the original secret that's sent is called the pre-master secret, and we use that to generate a master secret from which we can then split that secret into several separate keys for different purposes. So, broadly what happens here is that there's something called a handshake. Excuse me, sometimes I'm going to be a bit slow with the interface here. So we start off with a handshake, and the purpose of this handshake is a kind of setup of the TLS session. So maybe we can just draw a little kind of a line there. So a handshake consists of several messages which the client and server send to each other, during which process they're agreeing with each other. How are we going to encrypt our traffic? So they have to agree on things like what kind of symmetric cryptography are we going to use, what kind of asymmetric cryptography are we going to use, and once they've made sufficient agreements, then this very key message, which I'll give a different color, a very key message, a very important message called the client key exchange message. Client key exchange message is sent from the client to the server, and this message is encrypted with the asymmetric, well, not the whole message, but specifically the pre-master secret is inside this message, and it itself is encrypted with the asymmetric public private key. Sorry, what is I'm not used to this, I apologize. With the asymmetric public private key pair which the server has. So a big part of TLS, which I haven't got time to go into now, is the fact that the server has this public and private asymmetric key pair, and what the client is doing is sending this pre-master secret in here encrypted with the server's public key. So because it's encrypted with the server's public key, it means that when the server receives it, the server can decrypt it with his own private key, which only he knows, and he's never sent it over the wire. That's the whole idea of public key cryptography being used here. So crudely, once all the agreements have been made, so the client and the server have agreed the type of asymmetric cryptography, the type of symmetric cryptography, and a few other details, the client sends the pre-master secret encrypted with the server's pub key. The server then takes that encrypted pre-master secret, decrypts it with his private key, and at that stage both the client and the server have a pre-master secret which they have agreed on. Now, what is this pre-master secret? Obviously it's like a password. It's a secret set of information. The exact format you've probably already noticed is at the bottom here. It's basically 46 bytes of random information, a random number, so I've written kind of example in hex here, and there's a version bytes at the start. 0301 means TLS 1.0. So that is about as high level as I could make it of what happens in TLS. Of course, I haven't quite finished, because I should tell you also what is going on after that dotted line. So below that dotted line, what is happening is that traffic, actual encrypted traffic, is passing between the client and the server. It will be things like client requests the resource located at index.html, and server sends back the content at the location index.html using HTTP, but all of the traffic, every message, every HTTP record is encrypted using, no longer using this public-private key pair that we mentioned before, but now it's encrypted using the symmetric crypto key that was derived from the PMS. So both sides getting the PMS are going to use it to generate a symmetric crypto key. So that's not exactly the full details. So an example might be AES. So in AES, symmetric crypto, you have one key. That key is used to both encrypt and decrypt messages between the parties. There are other. It doesn't have to be AES. It can also be algorithms like RC4, and there are others. So both sides are going to generate this symmetric key, and the detail I haven't told you yet is actually there's more than one. There's more than one symmetric key, and there's some other secret data that's associated with the whole we call cipher suite. But let's just say it's symmetric keys for now, and as we said before, yeah, it can be AES, it can be RC4, or whatever. So all that traffic is encrypted with that symmetric key that nobody else could possibly know, because it was never passed over the wire, or rather the pre-master secret which is used to derive it was never passed over the wire. Excuse me. Okay, that gives you a good overview of the basic. It shows you TLS at the level you need to understand it in order to understand the next parts. Now, to understand the next parts, I think it's fair to say we need to start thinking about a little bit more detail how TLS generates these symmetric keys that we mentioned. So to do that, I think I've somewhere pulled up the yeah, this is the RFC. I hope this shows up okay on the screen. Just make it a little bit bigger. And in section 5 there's a rather detailed explanation of, if I can find it, 5, how the TLS works. So obviously pseudorandom here means we're generating random numbers, but we're doing it algorithmically, so we're not using some hardware randomness or something. We're using well-established methods for generating random numbers using algorithms. So here it's actually called HMAC and the pseudorandom function, because both of these are important. The pseudorandom function is built out of HMAC. So before we go any further, we need to know what HMAC is. I think I'll show you this in the notes first. So what is HMAC? Very crudely, HMAC is a way of, oops, that was not intended. HMAC is a way of creating a keyed hash. So I'm not going to go to the level of explaining a hash function. I hope you know what that means. So hash functions, usually we're going to have some data x, we're going to put it into some algorithm, it's going to output some fixed length data which is not predictable but which is deterministic. Now it turns out there are some limitations with using hash in this simplistic way for certain applications. For example, suppose we wanted to use this kind of construction where we take the data X and we concatenate it with a key K, or a secret key, let's say. And this would have the advantage that only a person who knew the key could generate the hash. So this would provide a kind of authentication. The concept being that if only parties A and B have key K, then only they would be able to generate this hash in the right form given the data X. However, this can have some limitations. In particular, the idea of a length extension attack is where you take that output, HKX, and you feed it into the hashing algorithm, and in some cases it may allow you to do something like this, where you then concatenate data Y. It's a little involved, this, but basically it means that if you think of the hash function as a kind of state machine, if you're given the output of the state machine here, ABCD, you can reverse that process from the output, which is sometimes called a digest, and revert back to the internal state of the state machine H. At that point you can then append the data Y and create a valid output of HKXY. This means that you can generate an authenticated version of this algorithm of X concat Y, even though you never knew the key K. This means that this is a bad authentication. This is a bad way of authenticating hashes, if I can put it like that. So this is sometimes called, well, it is called a length extension attack. And the reason I mentioned this mainly is this is why this kind of form is not used to create authenticated hashes. Of course, the idea here is that you can authenticate. You can say, yeah, I'm sending you the hash of X, but you know it was me because only I know K, or only I and you know the key K. So that whole process doesn't work because of length extension attacks. So the way HMAC is actually constructed, let's say the way that HMACs are currently constructed, because there may be some difference with, let's say, SHA-3, is the way HMACs are currently constructed is obviously not HX and not HKX, but something further. What we do is we make a construction something like this. So you can see here what I'm doing is taking the hash of the key concatenated with the hash of the key concatenated with X. And the idea of doing this is because this part is a hash, it can't be predicted in advance. So if you were to try to append, because this hash is inside this hash, it means that a person, Eve, snooping on this hash is not going to see this value, and so will not be able to perform the length extension attack. So that's the general idea of HMAC, and I'm not actually sure I needed to tell you that, but it does serve the purpose of emphasizing why HMAC is used, and that turns out to be very important in TLSNotary. So let's just look here for a little confirmation. The way HMAC is actually calculated is slightly more complex than what I said. There is this OPAD and IPAD, I think outer padding and inner padding, included in the construction. But apart from that, you can see the same structure: HK, concat HK, concat M, where M is the message, and also using XOR inside there. So what's the purpose? The purpose is authentication. It's called a keyed hash message authentication code. So that gives you an overview of HMAC. And let's go back now to the RFC, and we see how HMAC is used. First of all, two different hashing algorithms. These are quite old hashing algorithms, MD5 and SHA-1, are used in generating pseudorandom data in TLS 1.0. Here they don't say key but rather secret, but it's the same idea. So we've got those two hashing algorithms. Okay, so slight pause there, apologies. Yeah, so what the pseudorandom function in TLS does is it uses HMAC in order to create a stream of random or pseudorandom bytes. And as I was just saying, two different old hashing algorithms, MD5 and SHA-1, are used. And the idea is that for each of those two hashing functions, you create something they're calling here p-hash, which can either be pMD5 or p-SHA-1, and you can create as many bytes of randomness as you need based on a kind of recursive process. What you do is you start off by calculating a function they call A, and you do this by simply doing HMAC, that particular hash function, on a set of data. And that set of data for the first round is called the seed, so that's A0, the seed, that's what you start off with. And after that you calculate A1 by doing the HMAC with the same secret key, but the data now is A0. And for A2 you get A2 by doing HMAC of the given hash with the given secret on A1, and so on and so forth, as illustrated in this equation here. So that allows you to use any particular hash function to generate as much as much random data as you need, starting from a given seed and using a given secret HMAC key. So that's already a bit complicated, but they actually do, there's another level to it, excuse me, which is explained here. TLS's PRF, pseudo-random function, is created by splitting the secret into two halves and using one half to generate data with one hash, pMD5, so going through that process for MD5, and the other half using SHA-1, so going through that same process here with SHA-1. And you iterate this process here as many times as you need to in order to generate as much random data as you need. So let's say you need 40 bytes of random data. You do this process for MD5. Now MD5 has 16 bytes output, so you're going to need to do this. First you get 16, then you get 32, then you get 48. So once you reach 48 you stop and you discard the last 8 bytes and you've got 40 bytes of pMD5. And then you do exactly the same thing for SHA-1. You've got 40 bytes coming out of SHA-1, so you've got 40 bytes of pMD5, 40 bytes of p-SHA-1, and finally the last step is to XOR. Okay, so this equation is so important that I put it sort of pride of place in the main algorithm documentation. This is the algorithm here. So using that p that we just looked at, we do pMD5 XOR p-SHA-1. So this, as I've explained here, is a very critical property which we exploit in TLSNotary. It means that if the final result that you're getting is intended to be used in many parts, so for example, suppose you used this process to generate 40 bytes of random data. If you wanted only one party to get the first 10 bytes of that, and you wanted the other party to get the last 30 bytes, well, you could achieve that, couldn't you? And let me maybe illustrate that with a diagram, if I can. So you've got party 1. Let's use the old chestnuts of Alice and Bob. Let's suppose Alice has Alice calculates pMD5 of some data, and I'm going to use a comma 40 here to indicate that she's generating 40 bytes. So she's got, how do I write this? Maybe I'll just draw a rectangle. You'll find my drawing skills are somewhat limited. It seems to be a parallelogram, doesn't it? And Bob does the same thing. Now, of course, that does depend on knowing the, let me get this right, the secret, as we described in HMAC. HMAC has this secret key, so you need to know that, but we'll see in a minute that's not really a problem. So he does the same thing. Now, these two data sets, think of these as 40-byte strings. Because we're going to XOR them, that means that we can easily partition this data set. Let's say this is 10 and this is 30. What we can do is Alice can give to Bob, let's say, for example, just that way around, her first 10 bytes. So she's not giving the whole thing, because that would give away the whole resulting secret, but she gives the first 10 bytes to Bob so he can output the correct first 10 bytes. And Bob can give to Alice contrary-wise, he can give the last 30 bytes, and she can output from that the last 30 bytes of the final result. So this XOR process gives rise to the possibility of a kind of partition. And for some applications that will not be of any interest, because you might actually need the final result in its entirety, but in TLS that's not the case. So maybe I'll just tick these off because we've kind of covered what we needed to about those things. But in TLS it turns out that that's kind of exactly what you need to do. You need to partition the final resulting data into different sections. So that creates this possibility, which we are now going to exploit, of splitting the final set of keys. So let's just take a step back for a moment. At the moment we already have covered the basic concepts of TLS1, and we very briefly looked at the PRF, although you'd really need to read it in a bit more detail to understand it better. Now, how does TLSNotary split the secret? Now, this is complicated enough that I think I'm better off just sticking with the diagrams I've already drawn. The trick of it is that TLS does two steps of this PRF function to get from the original premaster secret to the final keys used for symmetric encryption. So the first step is illustrated in this diagram. It just about fits on the screen. So first of all, we start off with individual secrets. Audity has a certain secret, let's say 24 bytes. Auditor has another secret, 24 bytes. Excuse me. So here you see the first step is to do on the auditee side, let's say, it doesn't really matter which side, auditee side PMD5, auditor side PMD5 and auditee side P-SHA-1. Now remember that because of that recursive process you can generate as many bytes as you want, so what we do is we generate 48 bytes on both sides. And just to sort of recap, usually in normal TLS all of this will be done on one machine, but we can do it on two separate machines. So the auditor generates his first P, PMD5, and auditee generates his first P, P-SHA-1. Then they do this splitting as I just illustrated, where the auditee hands over, the auditee hands over the second 24 bytes of his resulting 48 bytes from that p-hashing process. The auditor combines that 24 bytes that he was given by the auditee, marked here in blue, with his own 24 bytes from the second half of his own PMD5. Then he XORs those two, and what he's going to get is the second half of the master secret. So the master secret is an intermediate step of secret data which is then used to generate the symmetric encryption keys. And you can see on the left here at the bottom exactly the same process being used to generate the first half of the master secret for the auditee. So you notice that the key point here is that at this stage neither the auditor nor the auditee has the entire master secret. And why that's important is because if you have the entire master secret, as a client usually would in TLS, you are then able to generate all the symmetric encryption keys. Which means if you have all the symmetric encryption keys, you can generate any kind of traffic you want. Traffic from the client, traffic from the server, whatever. So we'll get into that in a minute, but let's just complete the thought here. The second stage, now remember, auditor got master secret 2, second half. Auditee got master secret 1, first half. So what do they do with that? They do this, which is kind of the same thing all over again. Well, as you can see, it's not exactly the same. So now we do the p-hashing process again. And notice here the difference is we're still starting off with 24 bytes, but we're generating a much bigger set of data, 140 bytes. Actually, it's a little lower than that, but that's not important. The two sides generate their p-hash values, and at that stage each side has 140 bytes, let's say, of secret data, and they know that if they XOR that secret data with the other side's secret data, they're going to get the full set of data that is used for the symmetric encryption. But here's the trick, and to explain this trick, I think I should mention now this very important detail of TLS. Did I mention it before? Not really, no. Okay. Yes, here we go, right. So this is just another much simpler view of the same thing. The auditor starts with his first half of the pre-master secret, 24 bytes, and the auditee also 24 bytes. They generate their p-hashes. By generating their p-hashes, they are able to give each other one half of the master secret using this XOR trick. So let's say, so that would be auditor, wouldn't it? This MS1 would be given to the auditor, and the MS2 given to the auditee. So both sides at that stage have half of that secret, and they know that the other side doesn't have their half. But the second stage of generating symmetric encryption keys is that you do this p-hash process again, where you XOR a PMD5 and a PSHA-1 just as before. But what it generates, as I was showing on the other diagram, is this approximately 140 bytes, or less realistically, of secret data. And this is what we call the expanded keys. And expanded keys contains several secret bits of data. First, there are actual encryption keys. As you may remember earlier, I said that in symmetric encryption, the encryption and decryption keys are the same. So anyone who has this, the client encryption key, can read, can both decrypt and encrypt data that's valid as data from the client. And the same goes for server encryption key here. The MAC key should probably really be called HMAC key, because obviously we're talking about HMAC again here. But in the documents they usually call it MAC key or MAC secret or MAC write secret sometimes. But it's this same thing again with HMAC, where you want to make a hash, but you need a secret key in order to make a valid hash. So the expanded keys does not only contain one key, and it does not even only contain two keys. Now there are good security reasons why the client and server encryption keys are different, to do with replay attacks and other things I forget. But anyway, just take it as a given that the client and server use different encryption and decryption keys for the traffic that they send to the other side. But they also need this special HMAC key, and the purpose of the HMAC keys is to authenticate the traffic. Because when I send, let's say I'm a client, and I send to you, the server, my request, it's encrypted, great. But if it's not authenticated, then you may be getting requests from the wrong party. Somebody could have jumped into the communication and started replaying requests. Okay, that's slightly less dangerous. Maybe somebody's replaying server responses, which is a lot more dangerous. But in any case, we certainly want it to be the case that we're getting both privacy and authentication from TLS. We want to know we're talking to the right party, and we want to know that the traffic has not been tampered. So it prevents against forgery, prevents an attacker from changing some bytes in what is being sent, and it proves the origin at the same time, proves who it was that sent it. So that's why we get these expanded keys. We don't just want one key, we want client and server encryption keys. We also want client and server HMAC keys. Now the last two are a kind of technical detail, and they're not used, as I remember correctly, they're not used for every cipher suite, but for some cipher suites we want an initialization vector which is necessary to carry out the symmetric encryption and decryption properly. In particular AES uses this, not RC4 for example, but so be it. So in total there's usually 6 different bits of secret data embedded in this expanded key. So you have to think of the expanded keys as a very long set of 140 bytes partitioned, and it's partitioned in a prearranged sequence that's specified by the protocol, by the RFC. I think it's something like client encryption key, server encryption key, client MAC key, server MAC key, client IV, server IV. So in normal TLS, both sides go through this whole process on one machine. At the end, they can partition this final expanded keys result into the requisite keys. But what we're doing in this diagram, the second diagram I showed you, is following that process but on 2 machines. So these red dotted lines, by the way, I didn't mention on the first one, indicate this is the physical boundary between the 2 machines, right? So these are separate. So we start with a master secret, half on each side. We do our p hash. We generate 140 bytes of expanded keys. You see here 120 plus 20. Excuse me. Sorry, I jumped. That's wrong. Each side has their p hash, which is of the right size. And in order to create the expanded keys, you would need to XOR this whole thing, this whole 120 bytes here, and this whole thing here. But we use that same XOR partitioning trick, and what we do is the auditor gives, let's say, all the data, or let's say all the last 120 bytes, which contains all the required data to generate the client, the client HMAC key, the client encryption key, the server encryption key, and both, the IVs, the initialization vectors, but he withholds. So this one in grey here, the server MAC key, he does not send this to the client at the start of the session. So what does that mean? Let's think about the implications of that. It means that when the client starts sending his TLS traffic, specifically when he sends his first request, such as get index .html, yeah. So he sends some HTTP request to the server. He's sending that request in full possession of all the requisite keys except for the server MAC key, which authenticates the MAC traffic, the server traffic. So when he gets the response to that, the 200 OK and all the data, when he gets this back from the server, he doesn't have the authentication key, so he can't actually be sure cryptographically that what he's getting is a valid server response. So this in itself is, you could say, a security hole. So how do we deal with that security hole? Well, this is what we do. We receive the response, but then the client sends a hash of that response to the auditor. So hash here is performing the function of commitment. It's saying, I've received this data, I'm going to give you the hash, I'm not going to give you the original data. But later, when you ask me for the data, I can prove that it corresponds to what I sent. And I can prove it because when I send you the real data, you will also be able to hash it, get the same result. This is basically the most important property of hash functions, because you can't do what's called pre-image attacks. You can't generate fake data that happens to have the same hash. So, the client makes the commitment. After the client has made the commitment, as we show on this diagram, the auditor then sends the final 20 bytes, which can be XORed with the auditee's own 20 bytes coming out of his phash function, and he can get the valid server MAC key. Having received the valid server MAC key, he can decrypt the traffic, and crucially, he can authenticate it. He can check, yes, it hasn't been tampered with, and yes, it definitely came from the server. Now, you might argue, but can't the auditor screw this up? Can't the auditor modify the traffic that he receives? I mean, obviously it'd be a difficult hack to carry out, because after all, the auditor knows these 20 bytes. Well, after all, don't forget, the auditor doesn't know the auditee's 20 bytes. So this is the whole this is what's great about this XOR trick, is that each side at any stage has the opportunity to give to the other side some secret data without he himself getting that secret data. So that's why only when the auditor sends the 20 bytes of phash that allows this XOR to create the real server MAC key, then the auditee will check, okay, does this actually give a valid HMAC for my server traffic? If it does, he knows everything must have gone correctly. Nobody could have fabricated that. The server couldn't, an external attacker couldn't have fabricated it, and nor could the auditor. So what I've just described there is probably the key to the whole thing. It enables the auditor to know that the traffic that the auditee is claiming to have come from the server did in fact come from the server, because he could not have fabricated a valid HMAC without knowing those 20 bytes that I showed you just there. So as long as the auditor kept those away from the auditee, so to speak, the whole thing could not have been faked. So that's the key to the whole thing. But unfortunately, there is an extra fly in the ointment, and to see that, we go back to this horrendous mess which I drew here, because you probably remember we talked about at the beginning the client wants to send the premaster secret to the server without exposing it on the wire, so he encrypts it to the server's public key. Now, what I've just described, it would clearly be impossible to do this, because the auditee, who is functioning as client, does not know the entire premaster secret at the beginning of the traffic. Because if he did know the entire premaster secret, then he would also be able to calculate the server MAC key, which would enable him to fabricate the traffic. So we have to find a way for the client to send the encrypted form of the premaster secret to the server without knowing it himself. How is that possible? The answer is it's possible with something called homomorphic encryption. So what's homomorphic encryption? I won't tell you. That's a complicated topic, but I will just show you specifically what homomorphism means in this case. Now, shall I just maybe... Yeah, so before I tell you how it works mathematically, let me show you this high-level schematic. The idea is that we've split the premaster secret, remember, into two halves. So the auditor, who's marked in red here, is going to, after following the algorithm we've just seen, so that's what I mean here by exchange hashes. I mean, we've gone through that whole thing with pSHA-1, PMD5, we swap, blah blah blah, we XOR, and so on. At some point, the auditor will be able to send to the auditee the RSA encryption of PMS1. And what the auditee is going to do is combine the RSA encryption of PMS1 with the RSA encryption of PMS2, which he knows. So I've put in here in quotes "and" because we're going to see in a minute the mathematical basis for combining those two RSA encryptions to give the actual full RSA encryption of the full pre-master secret, which can be sent to the auditor. And the end result, as we see here, is that the auditee does not have the server MAC key when he receives the server response, and so he can't fake the server response. Okay, so last step, I suppose, no, not quite the last step, is to see mathematically how that's possible. So the basic idea of RSA encryption is that you take a message M, you raise it to an exponent E, and you calculate that mod n, where n is the modulus of the public key. So this is actually a very large number. It's about, it can be, for example, about 300 digits decimally, 256 bytes, 2048 bits. It can also be bigger than that, 4096 bits. And it turns out mathematically that if you take a message M, so just some data, just take some data, you raise it to a power E. Now E is usually 65537 if I remember right, but it can be other numbers. It turns out that if you do that, the reverse process of finding M given this, so if this is equal to X, then going from X to M is basically impossible. That's the mathematical sort of basis for RSA, and there's a lot more to the mathematics. For example, the modulus n is the product of two primes and so on and so on, but we don't need to go into that. But because we have this kind of mathematical structure, we can see easily that if we take two messages and we apply this algorithm, this encryption algorithm, to both of them, and we multiply them together, and we should also just mod n as well, the result we're going to get is going to be the same as this, just by the basic laws of arithmetic. And so this is sometimes called a homomorphism, which is kind of a clever word for it, but it's a simple mathematical property, which means that it's also sometimes called a malleability. I'm not entirely sure what that's all about, but the idea that you can change messages. But it means that, if you think about it, it means that we can perform multiplication under encryption. This is the kind of holy grail of homomorphic encryption. Multiplicative? I meant multiplication, sorry. We can do multiplication under encryption. So in other words, if I've got a number 7 and you've got a number 6, I can send you the encryption of my number 7, and you can combine it with the encryption of your number 6, and you'll get the encryption of 42 without ever knowing what number it was I sent to you. Of course, so this has huge implications in terms of private data computation. But obviously it's a huge topic, and there's a lot more to it. But for now, we just observe that RSA has this one nice homomorphic property, which we can write maybe in more general terms. RSA X times RSA Y. As long as we stick a mod n on there, we'll get RSA XY. So that's great. That's very interesting and useful, but it's not quite what we want, because if you remember, we were starting with a pre-master secret, 48 bytes, and we were splitting it into two parts, one for the auditor and one for the auditee, PMS1, PMS2. Unfortunately though, that means that we're taking some list of bytes, maybe there's a list of 4 bytes, and what we're doing is we're splitting it into 2 parts. So if you think of it more like numbers, it's not really correct to see this as a multiplication, is it? Because if this is PMS1 and this is PMS2, then these are the kind of the higher order bytes. It's a bit like writing a number, like just think of it in decimals, 86,430, 864,321. All right. So if I split that, the first half is the higher order bytes. It's 1,000 times 864. It's certainly not the case that this is in any way related to a product. So we've got a problem here, which is that if we want to use the RSA homomorphism to combine the 2 halves of the master secret, we can't do it in a naive way. It doesn't work. So without going into too many gory details, how do we manage to combine them anyway? Well, it is mentioned in the algorithm document that I showed you, but it's just based on the following observation, which is that if you take a number like this, let me get this right, 1200 times, let's get this right, hang on, 3400 0000, yeah. So if we take something like that, now let me just give me a second to calculate that. Okay, sorry, I just remembered rather basic and important error there. So the idea is not to put zeros, but to add 1. So if we just quickly edit that, so put a 1 on the end, and if you're wondering where I'm getting these zeros from, the idea is that is 4 digits. So if we put 4 digits there and 4 digits there, we get what we want, and the result is let me just read it again. 408. So we get 408 3400 1201, and let me just double check. Yeah. So I hope you can see that there's something very nice about this. The last 4 digits have not changed from here. Oops, that's supposed to be an arrow. Anyway, and these 4 digits have been preserved exactly here. Now, of course, these 3 digits at the front are some random, not random, but less deterministic, shall we say, coming as a result of multiplying 12 and 34 and what have you. So what this effectively does is it creates a situation where, although we're multiplying, we're preserving the digits in the original multiplicands, if that's the right word. So if you want to play around with that mathematically, obviously we're talking about, this kind of structure, or perhaps more accurately, you should put some powers of 10 in there, x times 10 to the k, y times 10 to the something else, and so on. So that mathematical trick is critical, because what it allows us to do is to achieve the result desired here, which is that the auditor can send to the auditee the RSA encryption of something like, so how would it work here? It would be something like RSA, which way round do we do this? Well, it doesn't really matter. Let's say the auditor sends that, and the auditee takes that. Now, he doesn't know the number because it's RSA encrypted, but he takes that and he multiplies it by his RSA encryption of this little thing here, and he gets the RSA of something like padding, concat, PMS1. It's actually the other way around here, isn't it? Concat PMS2, concat PMS1. Okay, sometimes you have to pay attention to these ones, of course, but you get the basic idea. So that crudely is what we do. There's a lot of extra details to worry about, in particular the padding, how the padding is structured to make sure that it's the right kind of structure to allow it to be an acceptable RSA encrypted message, because actually these RSA encrypted messages have to conform to a standard called PKCS version 1.5. So there's quite a lot of fiddling going on to make that work, but that's the basic idea, and you can investigate the details of the padding as they're laid out in the algorithm document. So yeah, we're nearly finished now. What we've seen is that we've seen how TLSNotary splits the secret. It's based around XOR. It's based around the fact that because we're making two hashes and XORing them together, we can kind of withhold parts of the secret between the two parties. And then there's the fact that how we send the client key exchange message, it's using RSA homomorphism, which means taking two numbers, multiplying them together, and sending the RSA encrypted versions of those numbers to avoid exposing them to the other party. Now there is an additional point about the finished message in the SSL handshake or the TLS handshake. I haven't even mentioned that. To be honest, let's not get into that now. It's still basically using the same trick, the XOR trick. So if you look into the finished message, and in particular how it uses hashes of previous handshake messages, it's a bit involved, but you can do the same trick. So the last thing to cover is commitment of server response, because now actually, to be honest, I've largely covered this already, but it might be worth emphasizing it because of the security issues. So the security issues here: if the auditee does not have the server HMAC, it means that he cannot authenticate the data that he gets from the server. See, this is the kind of trade-off thing here, right? We're saying that the auditor is going to check whether the auditee is lying. To do that, he's going to prevent the auditee from being able to generate fake data which is valid. And the way he prevents that is by withholding the information that the auditee would need in order to generate valid fake data. And that specific data is the HMAC that is appended at the end of a TLS record. I just realized I never mentioned that. When in TLS, when you send data, you're sending it in a record. And the record consists of all the data. So this will be HTTP data. It could be a request, could be a response. You might have a HTML file in here. But at the end of the record, it appends the HMAC, and the HMAC is 20 byte SHA-1 based HMAC. So think of it as HMAC using server MAC key or client MAC key as the secret. Then you've got the data, and the algorithm is SHA-1 always for TLS 1.0. So because when the client receives his TLS records, he's got all this stuff. When he looks at this hash, he can't verify it, he can't do this process because he doesn't have this data. So he doesn't really know that that data has come from the server, except that it would be difficult to, obviously, at the network level it's difficult to inject data, but it can be done, right? And he also doesn't know if, even if it is really data from the server, maybe it had some extra data appended or subtracted or modified. unless he can check that MAC. So that's why we say here he can't check the server MAC. So that's not safe for him to then decrypt that data in his browser, let's say, and say, oh yeah, okay, let's read this data, and it's got some dodgy link or some dodgy JavaScript which hacks him to death. All right. So that's how we use a commitment. So let me just reiterate what I already mentioned. 3 parties involved, right? There's the server. The server sends the response to the auditee. The auditee takes that response, hashes it, and I think we use SHA-256 to hash it, but it doesn't really matter. And he sends that response to the auditor. He sends that hash to the auditor. So the auditor now has a commitment as to what that response contains. Then the auditor sends the server MAC p hash. So just one more reminder, what he's sending here is specifically that little 20 bytes of data that allows the auditee to XOR and get the correct server MAC key. So he sends the server MAC data, let's say, to the auditee. Right, what happens next is the auditee decrypts the server response. So at this stage he can look at that data knowing full well he's got the full TLS security model. The data was privately sent and it was authenticated. Having decrypted the server response, he then decides whether he wants to send that data to the auditor, and if he does, he sends the response. And the final step, of course, is the auditor checks this revealing of the previous commitment. He looks at he calculates the hash, the SHA-256 hash of the response, and he sees if it matches with the earlier commitment. If it does, then everyone's happy. The auditee's got data which he's completely authenticated. The auditor has got data which he knows the auditee couldn't have faked, and that's the final sort of endpoint we were aiming at. So I've basically finished. Perhaps the final thing to mention is, about the restrictions to this whole model. The main restriction has already been mentioned several times, which is that this process only works for TLS 1.0 and 1.1, and in fact we haven't implemented it yet for 1.1 because there's a couple of technical details in the changes to the protocol which would need to be changed, but in principle that's definitely possible. But TLS 1.2 is not going to work like this. It may work in a different way, but not like this. And the final thing, of course, to mention, the other restriction also is because we're using the RSA homomorphism, we're restricted to RSA cipher suites. So cipher suites are really that negotiation I mentioned at the beginning between auditor and auditee in terms of what kind of asymmetric and symmetric encryption they're going to use in the session. Alright, so I'll leave it there. I hope that was interesting to at least somebody.